Hi everyone, welcome to class number 35 of Physics 218. Last time we continued our discussion about scattering from a potential energy step. Today we're going to wrap up our discussion of one-dimensional quantum mechanics with another example of a non-bound state, one that has some interesting real-world applications, namely tunneling through a potential energy barrier. To start off our discussion, I'd like to have you think about the following question. I haven't made up multiple choice answers for it, but think of this as a clicker question. So the situation in that question is not unlike what I've drawn here with a one-dimensional energy graph, where if we imagine we have the ball rolling and it has some kinetic energy K depicted here, and that hill is like this potential energy step that has a maximum height of mg y max. Now, if you think about classically what's going to happen in this situation, right? So here, right, at this point, all of the ball's energy is kinetic, right? But then, as it gets onto the hill here, because the potential energy of the system is going up, the ball's kinetic energy will go down, right? That gap between the total energy and my potential energy. And so, as you probably expect, the ball is going to slow down as it goes up the hill. There's going to be a classical turning point right here. Let's sort of mark that turning point right there. And then what you would expect is that the ball would, roll back down and head back to the left. Critically, right, there's zero probability, there's no way in classical physics that the ball would somehow magically make it to the other side of the hill. Now, we're going to analyze something that's quite similar in the context of quantum mechanics. To make the analysis a little bit simpler, we'll sort of idealize this potential energy barrier here, and we'll actually consider a case like this. So if I have this, and we'll have a potential energy, we'll consider something, just a barrier with straight sides and some height. We're going to call V naught, and let's call the width of this A. And then we're going to mainly focus on the case when we're going to look for scattering states as before, but we're going to focus on the case where the total energy is, so E is less than the height of my barrier. And what we're going to see is that in quantum mechanics, there is a probability for a particle incident from the left to be found on the right. In other words, there's a possibility for tunneling through this potential energy barrier. So to proceed, let's actually go to the PhET we've looked at a few times, and we'll sort of see what happens in action, and then we'll figure out how we might be able to analyze it mathematically. Okay, so let's see what's going on in this quantum tunneling and wave packets PhET. We have our potential energy in barrier mode, and let's start out by sort of considering physically what happens when we have something that could represent a particle incident on the barrier from the left, namely a wave packet. So let's just see what happens. So I think you can see that there is some probability of afterwards finding the particle on the right side of the barrier and on the left side of the barrier. However, right, as we've talked about, wave packets are the sum of lots of different plane waves. So because they have all different, they're an integral of a summation of different plane waves, a wave packet doesn't have a definite energy. That is, it's not an energy eigenfunction. So for mathematical analysis, it will be easier to look at the case of what happens with a plane wave. Now, if we start off with the plane wave with an energy above the height of the barrier, so we see that there's sort of not too much that's surprising. We sort of see very similar behavior before and after, right? However, and the higher up if I imagined I made my incident energy much larger than the height of the barrier, eventually I should get to a state where like that barrier basically isn't there. Things get interesting, however, if we take the energy of our incident beam and reduce it to below the barrier height v naught. And so now what we can see is that there's quite a different amplitudes and on either side of this barrier, that there seems to be some sort of decaying-ish behavior happening in the middle here. Let's just stop time here. You can sort of see this sort of decaying in the forbidden region. But, there is still some probability of finding my particle here to the right of my barrier. Namely, there's some probability for my particle to tunnel through. Now, we can play around with seeing what happens, for instance, if I make this barrier narrower. So with a narrow barrier like that, now you can see that there's the probability density here, or the probability of my particle tunneling through, is not as small as it was before. And so one of our goals will be to try to get some intuition for what happens if I either make the barrier very wide, in which case is not so surprising, we get very little transmission, or if we make the barrier, if we play with the barrier width, or if we play with the barrier height. So it's a little bit of a preview of what we'll be able to calculate. What we can look at is, what we can actually calculate is probabilities for reflection and transmission. And again, we can sort of play with those and play with sort of play around with the barrier height and width and the incident energy. We can sort of see how the probabilities for transmission and reflection change. So if I sort of make this a narrow barrier, now we have a much higher probability of transmission. So here's the setup we're going to analyze. We're going to assume a potential energy step of height v naught. So the potential energy is non-zero between 0 and a, but the potential energy is 0 everywhere else. We're also going to assume that we have a beam of particles, aka a plane wave, like we did for analyzing scattering from a step. We have a plane wave of a beam of particles of some energy E incident from the left. And we're going to explicitly assume that E is less than V naught over here. Now, like we did for the analysis of scattering by a potential step, what we need to first do is to write down the general form of solutions to the time-independent Schrodinger piecewise. So we have sort of 3 different regions, 1, 2, and 3 here. And what I'd like you to now do is think about what we did in the previous class, and think about what the form of the solutions to the time-independent Schrodinger equation might look like in regions 2 and 3. So let me just write that out explicitly for you. So if you answered that the solutions should be oscillatory in region 3, but decaying or exponential in region 2, that's that classically forbidden region, you would be correct. Let's see how this plays out in practice. So in region 1, right, our time-independent Schrodinger equation has the following form. It goes like d squared psi of x dx squared equals minus 2me over h bar squared times psi of x. And so our general, or I can write this as minus k squared times psi of x with k defined as usual as root 2me over h bar. And as you can probably guess, the solutions to this are going to have the following form. It's going to look like psi of x, and I'll stick in two arbitrary constants. So I'll have, I'll have an oscillatory thing, a e to the I kx, plus b e to the minus I kx. As you might guess, right, so this term here, we're going to end up identifying with our incident plane wave. It's a plane wave going that way. This term, we're going to end up identifying with our reflected wave, because it's a plane wave propagating in the minus x direction. When we add the time dependence. Okay, now in region 2, right, we have the following, right? So in region 2, we have d squared psi dx squared. This time, right, since e is less than v naught, we'll have a 2m v naught minus e over h bar squared times psi of x, and as we've done before, we can call this kappa squared psi of x. If we define a kappa, right, so if we have a kappa defined as root 2m v naught minus e over h bar, and then, right, this is going to give rise to real exponentials if we write down the solutions to this. But this time we have to be careful, and we've got to write down both possible terms. Namely, you should be able to convince yourself that either of the following satisfies the time-independent Schrodinger equation. Namely, I can have a term proportional to e to the positive kappa x, or a term proportional to e to the minus kappa x. Okay. Several remarks. So why f and g? So I'm just following Townsend's notation here. We don't actually need to call those f and g. We're just doing it because we're going to end up, if you mathematically solve this, we don't end up caring about f and g so much. So we're sort of we're going to save c for the wave function out here. So the physically important thing, though, is that we need to know both of these terms. Right? So when we analyze scattering from a potential energy step, right, for E less than V naught, we were able to reject this rising exponential over here, right, because we said that, well, this term, as x goes to infinity, this term blows up. We can't do that here, right, because this form is only valid in region 2, between x equals 0 and x equals a, and both terms of this wave function are perfectly well behaved between 0 and a. So we do have to hang on to both of them, so that's sort of the biggest difference from what we did last time. Now, in region 3, nothing shouldn't be too much of a surprise. So I'm gonna just have enough space here. So I'm not gonna bother recopying the form of the time-independent Schrodinger equation. I think you can see that it's gonna have exactly the same form as here. Now this time, when we write down the general solution, let me maybe label this as psi sub 1, psi sub 2 there to denote the wave function in each region. So this is psi sub Roman numeral 3. This time we'll use C, and we'll just have this proportional to e to the I kx. And again, and this time it's on physical grounds that we're only keeping this term. We know that we have our wave incident from the left, right? This term we're going to associate with our transmitted wave. So let's write that here. Transmitted with our transmitted wave. But since there's nothing incident going to the left from out here, we keep only the term proportional to our transmitted wave. So based on what we did in the last class, it might not surprise you too much to find out that the next thing we've got to do is to apply boundary conditions, right? We have the wave function in each of these 3 regions, and now we have to stitch these general solutions together at x equals 0 and x equals a. As we've discussed before, the boundary conditions we have to apply are that the wave function psi of x is continuous at 0 and a, and also that the first derivative, d psi dx, is continuous at those same points. So we have sort of 5 undetermined coefficients. We've got sort of 2 boundary conditions to apply at each of 2 places. So once again, this is going to be a little bit of an algebraic mess. I'll do a bonus video where I'll go through some of that. But at this point, we'll just jump to sort of what the physical results we get from sort of doing the tedious algebra are.